Picture a future where humanity has transcended Earth and ventured into the vast expanse of space, seeking new frontiers and resources to sustain our energy needs. Imagine a megastructure engulfing a star, capturing its immense energy. This is the Dyson sphere, a concept igniting imaginations. Named after physicist Freeman Dyson, it represents technological ambition, a testament to our desire to explore and innovate. Harnessing the power of a star becomes increasingly alluring. The scale and complexity of a Dyson sphere are mind-boggling. Imagine satellites and habitats capturing a star's energy. It's a concept that stretches our technological limits. Join us as we explore Dyson spheres and their possibilities. At the heart of the Dyson sphere concept lies a fundamental challenge: energy. Energy is the lifeblood of any civilization. The sun releases an unfathomable amount of energy. This sparked the concept of capturing stellar energy. The Dyson sphere is a giant solar energy collector. It represents a limitless supply of power. Imagine a future where energy scarcity is a thing of the past. This is the promise of the Dyson sphere, a vision of humanity harnessing the power of the cosmos. While the Dyson sphere may sound like a concept straight out of science fiction, its roots are firmly grounded in scientific principles and the very real challenges facing humanity's future. It's not just a fantastical idea but a thought experiment that forces us to confront the limitations of our current technology and the extraordinary lengths we might need to go to as a species to ensure our long-term survival and prosperity. The concept of a Dyson sphere challenges us to think beyond our current understanding of engineering, physics, and the very nature of what's possible. It encourages us to explore new frontiers of knowledge, to push the boundaries of innovation, and to envision a future where humanity's ingenuity knows no bounds. While the challenges of constructing a Dyson sphere are immense, the potential rewards are equally extraordinary. It represents not just a solution to our energy needs, but a symbol of humanity's ambition, ingenuity, and our unwavering desire to explore the cosmos and unlock its secrets. Join us as we delve deeper into the fascinating world of Dyson spheres, examining the scientific principles behind their conception, the technological hurdles we must overcome to make them a reality, and the profound implications they hold for the future of humanity. It's a journey that takes us to the very edge of our current understanding and invites us to imagine a future where the impossible becomes possible. The concept of a Dyson sphere, often attributed to Freeman Dyson, actually predates his involvement. Its roots trace back to science fiction, known for its boundless imagination. In 1937, Olaf Stapledon introduced the idea in his novel, Star Maker. He described a civilization harnessing solar power with orbiting platforms. This idea inspired scientists and futurists. It suggested advanced civilizations might harness stellar energy. Freeman Dyson later recognized its scientific merit. In 1960, Dyson published a paper giving it a scientific framework. He proposed advanced civilizations could build structures around stars. These structures would capture significant portions of stellar energy. Dyson's paper was a thought experiment, not a prediction. It explored potential technological capabilities of advanced civilizations. Dyson suggested searching for infrared signatures to detect intelligent life. Section 2. Dyson's Vision. A thought experiment in energy. Freeman, Dyson's seminal paper focused on the energy implications of a megastructure around a star. Stars, as colossal fusion reactors, are the most abundant energy source in the universe. Advanced civilizations would eventually need to harness this energy. Dyson envisioned a network of orbiting structures capturing star energy. This thought experiment explored energy consumption limits and potential solutions. Studying star energy signatures could detect Dyson spheres, hinting at extraterrestrial intelligence. Dyson's idea sparked interest in SETI and the search for advanced civilizations. The Dyson sphere became a symbol of humanity's cosmic curiosity. Section 3. The Kardashev Scale. Measuring Civilizations. The Kardashev scale classifies civilizations by energy consumption and technological advancement. Proposed by Nikolai Kardashev in 1964, it includes 3 types. Type 1 harnesses planetary energy. Type 2 harnesses stellar energy. Type 3 harnesses galactic energy. The scale highlights energy's role in technological advancement. Section 1. The hunger for energy. Humanity's thirst for energy is insatiable, driving progress and development. From ancient campfires to modern cities, our reliance on energy has intensified. Technological leaps demand ever-increasing power. As we explore space, our energy limitations become clear. Fossil fuels are finite and harmful to the environment. Renewable energy faces scalability challenges. Our energy demands will continue to soar. We need sustainable, abundant, and clean energy. Failure to address this could threaten our survival. A Dyson sphere could harness immense power. It represents a future of energy abundance and technological advancement. Beyond fossil fuels. The quest for sustainable power. The transition from fossil fuels to sustainable energy is a societal imperative. Our reliance on finite, polluting energy sources leads to climate change, air pollution, and instability. We must embrace clean, renewable energy solutions. Significant strides have been made in solar, wind, and geothermal power, but they face limitations in intermittency, storage, and distribution. The sun doesn't always shine, the wind doesn't always blow, and transporting energy from remote sources is challenging. Even with widespread adoption, renewable sources alone can't meet future energy demands. As humanity expands beyond Earth and establishes colonies on other planets, our energy needs will dwarf current levels. We need a transformative energy solution, one that provides limitless clean power. The Dyson sphere, harnessing a star's energy, embodies this vision. A star's potential, the allure of limitless energy. Stars are colossal fusion reactors, converting hydrogen into helium and releasing unimaginable energy. Our sun bathes Earth in more energy in an hour than humanity uses in a year. A Dyson sphere could capture this stellar energy. Imagine harnessing even a fraction of a star's energy. It would grant limitless power, fueling cities and space travel. Energy scarcity would be a distant memory. The allure extends beyond solving energy woes. It symbolizes humanity's ambition to reach for the stars, a testament to our desire to explore and innovate. The challenges are immense, but the rewards are extraordinary. A vision of a future powered by cosmic energy, unlocking technological advancements, and exploring the universe. The Material Mountain, an astronomical construction project. Constructing a Dyson sphere would require an unfathomable amount of raw materials, a quantity so vast that it dwarfs the combined mass of all the planets in our solar system. Even if we were to dismantle every asteroid, moon, and planet, we'd still fall woefully short of the materials needed to encase our sun in a shell of solar panels. To put this into perspective, imagine trying to build a skyscraper out of toothpicks. The sun, while just a medium-sized star, is absolutely colossal compared to even the largest planets. Enclosing it in a sphere would require a surface area billions of times larger than that of Earth. Where would we even find this astronomical amount of matter? Some have proposed mining the asteroid belt, but even that vast collection of space rocks pales in comparison to the sheer volume of material needed. Others have suggested harvesting resources from other star systems, but that would require technological leaps in interstellar travel and resource extraction that are currently beyond our reach. The material challenge alone presents a seemingly insurmountable obstacle to constructing a Dyson sphere. It's a stark reminder of the vastness of space and the limitations of our current technological capabilities. Even if we could somehow muster the resources, the logistics of transporting and assembling such a mind-boggling amount of material in space would be a logistical nightmare of epic proportions. Section 2. Gravitational gymnastics, maintaining orbital stability. Assembling a Dyson sphere around our sun is a monumental task. Keeping it from collapsing into the sun is even harder. Immense gravitational forces could send it spiraling into the sun. It's a delicate balancing act. The sun's gravity constantly tugs at its inner surface. Perfect balance is needed to counteract this pull. Maintaining equilibrium is a constant battle. Minor variations could disrupt the balance. Imagine a spinning top beginning to wobble. That's what could happen to a Dyson sphere. A collapsing Dyson sphere would be catastrophic. It could release unimaginable energy, sterilizing planets. Section 3. The fragility of megastructures, a cosmic balancing act. Even if we could somehow address the material and gravitational challenges, we're still left with the inherent fragility of megastructures in space. A Dyson sphere, even one constructed with the most advanced materials imaginable, would be incredibly vulnerable to impacts from asteroids, comets, and other celestial debris. Space, despite its apparent emptiness, is a shooting gallery of cosmic projectiles. Asteroids, remnants from the early solar system, zip through space at incredible speeds, their trajectories often unpredictable. A single sufficiently large impact could punch a hole through a Dyson sphere, disrupting its delicate balance and potentially triggering a cascade of failures. And it's not just asteroids we need to worry about. Solar flares, those bursts of intense radiation from the sun, could also wreak havoc on a Dyson sphere's delicate systems. Even micrometeoroids, tiny particles of space dust, could erode the sphere's surface over time, gradually weakening its structural integrity. Maintaining a megastructure in the harsh environment of space is like trying to build a sandcastle on a stormy beach. The constant bombardment of cosmic forces would require constant vigilance and repair, a monumental task that would strain even the most advanced civilization's resources and technological prowess. Section 4. Technological leaps. Bridging the gap between vision and reality. The challenges of building a Dyson sphere extend far beyond materials, gravity, and space debris. We'd need significant technological leaps in energy capture, transmission, storage, robotics, and AI. Capturing the sun's energy is just the first step. We'd need to convert, store, and transmit it wirelessly over vast distances. This requires breakthroughs in superconductivity, wireless power transmission, and energy storage. Constructing a Dyson sphere would need autonomous robots operating in space. These robots must self-replicate, self-repair, and make complex decisions. Building a Dyson sphere requires us to become a Type 2 civilization. This demands a fundamental shift in physics, engineering, and reality. It's a distant goal, a testament to human ingenuity and the vast gulf to science fiction marvels. While a solid Dyson sphere is challenging, a Dyson swarm is more practical. It consists of many smaller solar collectors orbiting a star. Each intercepts a portion of the star's energy. They beam energy to a central hub or planets. This approach is feasible, scalable, and resilient. Even with the more feasible approach of a Dyson swarm, the material demands for such a mega-project remain astronomical, at least by today's standards. We'd need to look beyond Earth, venturing into the vastness of space to unlock the virtually limitless resources hidden within asteroids, moons, and even planets. Asteroids, those remnants from the early solar system, are particularly enticing targets for space mining. They come in various flavors, some rich in metals like iron, nickel, and platinum, others containing water ice and volatile compounds essential for life support and rocket fuel. By harnessing these space-based resources, we can bypass the limitations of Earth's finite resources and fuel the construction of our Dyson swarm. Developing the technologies for efficient and economical space mining is crucial for realizing the Dyson swarm vision. This includes advanced robotics for autonomous mining operations, spacecraft capable of transporting vast quantities of materials across the solar system, and in-situ resource utilization (ISRU) technologies to process raw materials into usable components directly in space. The transition to a space-based economy where resources are extracted and utilized beyond Earth is not merely a logistical necessity for building megastructures like the Dyson swarm. It represents a paradigm shift in humanity's relationship with space, transforming it from a frontier to explore to a source of raw materials and economic opportunity, fueling our continued expansion and development as a spacefaring civilization. Constructing a Dyson swarm requires advanced robotics capable of autonomous operation in space. These robots, equipped with AI, adapt, learn, and self-replicate using asteroid materials. This accelerates construction, bypassing Earth's limitations. The potential benefits for humanity's space expansion are immense. Our robotic companions will shape our future as a spacefaring civilization. Gazing into the crystal ball of scientific speculation, we can sketch a rough timeline for humanity's journey towards a Dyson swarm. The first steps involve mastering space mining and resource utilization. Within the next century, we can envision becoming proficient asteroid miners. This paves the way for larger-scale construction projects in space. The following centuries will likely see significant advancements in robotics and AI. Self-replicating robots will be essential for assembling and maintaining a Dyson swarm. We might envision the first elements of a Dyson swarm within the next 500 to 1,000 years. The complete realization of a Dyson swarm, a colossal web of energy collectors encircling the sun, might be a project spanning millennia. It represents a testament to long-term thinking, a multi-generational endeavor requiring sustained dedication, innovation and collaboration on a scale rarely seen in human history. While the practical benefits of a Dyson swarm, such as virtually limitless clean energy, are undeniably appealing, the allure of such a megastructure extends far beyond its pragmatic applications. It represents a profound symbol of human ambition, ingenuity, and our relentless pursuit of knowledge and exploration. The quest to build a Dyson swarm, should we choose to embark upon it, would be a journey of self-discovery, pushing the boundaries of our understanding of physics, engineering, and the very nature of intelligence. It would foster collaboration and innovation across disciplines, uniting humanity in a common goal that transcends borders, cultures, and even generations. The Dyson sphere, whether a solid shell or a more feasible swarm, will likely remain a tantalizing what-if for the foreseeable future. However, the very act of contemplating such ambitious concepts serves a valuable purpose. It forces us to confront the grand challenges and opportunities that await us as a spacefaring civilization, encouraging us to dream big, push the boundaries of innovation, and strive for a future where the impossible becomes possible. As we conclude our exploration of Dyson spheres, we find ourselves teetering on the precipice between science fiction and scientific progress. The concept of enveloping a star to capture its energy, once confined to futuristic novels, has become a thought experiment of extraordinary proportions. The true value lies in the intellectual journey they inspire. By grappling with such audacious ideas, we expand the horizons of our imagination. The Dyson sphere symbolizes human ingenuity and our evolving cosmic relationship. It reminds us of the universe's vast, untapped potential, inspiring future generations. Contemplating such concepts nurtures wonder and curiosity, encouraging us to embrace a future full of possibilities. The universe awaits, and the future, while uncertain, is pregnant with possibilities.